Hello, hello. I'm on the live stream. Yeah, yeah. Nice. Not much. Not much. I recently discovered your video. It was very exciting. Nope, I did not. Yeah, there was no audio in the stream the whole time. I'm listening through the Discord stream.
Shit. Is that better?
Hold on, let me test. Let me test in a second.
Huh. Well, I think that's working. I think so. Oh, okay,
It's
cool.
working.
Okay. I think they can also hear the Discord through the stream, but that's okay. Let's see. Very nice. We don't hear you. Oh, my bad. Oh yes. So the Discord link was in the YouTube video, but I can just paste it right here. Oh my God, my computer's gonna die. Okay. Okay. Cool. Cool. Oh yeah, so basically, let's see, what was I talking about? Oh, yes. So, well, I might as well keep chat up while I'm talking about this, but basically for a motor controller that I want to make for my monowheel, you have your like three phase wires for your motor, which are like the 3 windings, and you need 6 switches to control like the voltage, and therefore, because there's, it gets a little strange, but because there's inductance, you can run like control loops to control basically the current through the three phases of your motor, and that makes it like do whatever you want it to do. And so, yeah, the first step is choosing the switches. And I was already doing some shopping today, and I came across these, which are very low on resistance, and my battery is 65 volts, and so, or 16S is like 60-70 volts, somewhere around there, and so it's rated for that. And oh yes, because I'm doing 12 kilowatts, well, I think it's working. Oh yes, okay. Because I'm doing 12 kilowatts, it's about 120 to 150 amps, and so these should be okay. Well, actually, if I put one of these, it's gonna get pretty warm because the conduction losses, because of this resistance, are pretty high. It's like 20 watts or something. So what you can do is you can put 2 of them in parallel, and you get half the resistance and therefore half the power loss, which is good. But the problem is, though, then they'll switch slower, but my switching losses aren't too high right now. Yes. Oh yeah, this is the motor that'll be powering. So yeah, I need to make, oh, and then, so whenever you're like making PCBs, I get all my PCBs from JLC PCB, and so you can get all different types of PCBs, like normal ones, high count, flex, but the one I'm curious in is, oh man, they don't even have it here listed. Let's oh yes, it's in this one, but it's basically aluminum PCB, and they use this for like LEDs that get really warm and stuff like that. But basically what it is let's see, it's like the normal copper on top, but it's just one layer, and it has a thermally it's like electrically isolating but thermally conductive dielectric, and then just like a chunk of aluminum on the bottom. So it's really good for dissipating heat, and I can basically have my power stage, like the big MOSFETs that are heating up a lot, on the aluminum PCB, and then mount that to a block of aluminum, and probably put some, like I might add water cooling. Who knows? I don't think I'll need to dissipate that much heat though. The main heat comes from the motor. Let's see. Here's like an example. See, like the copper on top and the bottom is like the aluminum. So these are great for thermally conductive stuff. And then they even have ones that are like more layers, but this is expensive. This is pretty expensive. Yeah, so GLC PCB just does one, but I should be able to manage everything with just one layer. So it works out perfectly. Let's see. Yes, this is still in the design phase. So I probably need to check chat more often. But so I'm trying to speed run this and finish it this weekend because I want to finish the whole vehicle in a few weeks, 6 weeks. So before like January, or before like December, before we leave for Christmas. Yes, heat sinks are pretty effective. I don't know if you were talking about the MOSFETs, but basically what it almost is a heatsink in a way, because these mount onto the circuit board, and then right underneath is the aluminum, which takes the heat from these, and then you have the like big aluminum block that like goes onto the back, and so that's what does heat sink the whole thing. And well, actually, if a big aluminum heatsink isn't enough, like for example, the big aluminum chunk is going to be probably behind the motor where it mounts, and there's probably going to be a bunch of fins here. So as you like start moving pretty fast, like the airflow goes through the fins, and so that might be enough. Or I might put some like radiators in the back and use like they have just like the PC radiators, and which are a little better than a heatsink because it's like, I mean, it is a heatsink that you push air through, and basically with one of these and then put a water cooling loop, kind of just like you do on a CPU, and then you get more heat dissipation. So that's the plan. Oh yeah. Cool. Oh yes. So what was I doing? I was going to look at okay. Yes. Cool. So usually whenever you're getting a circuit board manufactured, they give you tolerances to what you can manufacture to. So what I'm going to do, I'm going to make a new template. Hello.
Hi.
Dude, I'm live streaming my inverter design.
Oh, you are?
Yeah.
Cool. Are you Miguel?
Yeah.
Oh, cool. Okay.
Nice to meet you.
Nice to meet Jasper.
What you up to?
I'm just going to polish a piece of metal real quick.
Oh. Nice. Oh.
Nice.
Well, what's it for?
It's for my friend's birthday.
Oh.
That's his name.
Nice.
Infinity symbol with pi.
Oh, very cool.
Yeah.
Well, good luck.
Thanks.
See you.
See ya.
Let's see. Okay. Yes. So. Okay. So. Okay. Oh.
Oh, Miguel. Just want to double check. I can use the one on the right, right? It's polished aluminum. The
As
other
long
one
as
says
it
no.
works.
Okay.
Oh wait, the one on the
Right. The left says no aluminum. So I'm assuming the other one is yes aluminum.
I think in general using aluminum on that is
That.
probably not a good idea.
Oh, do you
I
think I
think-
can polish this?
I also think it won't necessarily polish it. It'll just
Scratch
like
it.
scratch it pretty bad.
Oh.
You probably want some really fine sandpaper that we might have
Oh.
over in the cabinet under there.
Thanks.
Yeah. Okay. Oh shit. Oh, shit. Alright. Oh, we have 10 concurrent viewers. Oh, hello everybody. Oh, we have 14. Wow, that's crazy. So, oh yes, so I'm gonna make a new template for these aluminum PCBs. Because then once I want to make more of the like aluminum PCBs in the future, it's just way simpler to do so. So, keep pressing that next one. Okay, cool. Okay.
Hey, sorry.
What's up?
Do you know how I can attach this?
Let's see. Oh, see, like this collet is. What's this one? Yeah. Maybe we'll use this one. This collet is smaller,
So it's not gonna fit.
so this one probably won't fit on that grinding wheel.
Oh, okay.
You might have to find one that's like of his size.
Okay.
But there might be adapters. Working on really use this before.
Oh, no, that's not so.
Oh yeah, but like for unscrewing, you basically like turn it into like.
Okay, thanks.
Yeah. Oh yeah, but those that are soft are the polishing wheels, like the one that you had. If it's like a soft,
It's okay.
like the round one. Yeah, like that
That's
one.
good.
I think that's something that polishes.
Okay, thanks.
Yeah. Okay. Oh, let's see. Oh. Oh, cheers from Spain. Wow. Spain's like a totally different time right now. That's crazy. Okay, let's see. Aluminum. Okay. Okay. Cool. So. Oh yeah, I changed the name of all these wrong. Oops. Cool. Oh. Oh, thank you. I'm 20. Yeah, I kind of procrastinated making that YouTube video, and then I finally got around to it. So, oh, that was nice. Because most people make them like when they apply, but I never got around to it. Well, I was just like, honestly, I was just kind of lazy to make it. And then, but there was this prize called the duct tape prize that some friends put up recently, and so I made that because if it was like a application, like you could get money possibly from if they liked your maker portfolio. So I was like, oh, you know, I could possibly get some money for it. Okay. Yeah, this is honestly pretty annoying of having to change all these file names, but the interesting thing is that, oh yes, I am making a, oh yeah, for context, just keep it right here. So I have my monowheel, that is this guy, and well, let me show it a little better. So this is like an electric vehicle, and it's just like a big wheel that you sit inside of, and I want it to go really fast. And so here, this is like a build space, and we have like a bunch of free stuff. And so I found this 12 kilowatt motor, which means if I can, well, technically you could buy a motor controller, but they're pretty expensive. And if you make it yourself, you can make it better and cheaper. So I was like, oh, why don't I make my own inverter? And so that's what I'm doing right now. Or you know, that's the plan at least. And so I'm just setting up a KiCad, which is like the like PCB design software that I use, which I think is pretty good software. It's very nice to use. Okay, so I think that should be it. If I just file, open project, let's see. Okay. Oh. Okay, yes. So I don't really care much about the schematic template here, but I do care about the PCB template. And so, let's see here. That's all I want. And the main thing here is back to, oh yes, back to here, is they give all this, all these specifications. And so I'm gonna go in here, oh not here, here, and first of all, this is the stack up. So usually your PCB is made out of like multiple layers, but in this case it's just one layer. And so what I'm going to do is, I think there's a way to oh, that just crashed. Oh, never mind. Okay, well, it doesn't support one layer boards, but my board is going to be just one layer. So I'll kind of just leave it at this and do that. Okay. And then okay. None of this really matters because these aluminum PCBs don't have silk mask, I don't think. Yeah. So that doesn't really matter. The main thing here is these like design rule constraints, which are gonna say like how far things are like manufacturable from each other. I'm gonna use the STM. I'll just type it. Like a G4 series, but I'm not sure which variant yet. Because some of them have more ADCs, so you can do like better sampling and stuff like that. So we'll see. Yeah. Nice slot. Okay. Hold hole clearance. Honestly, I don't think a lot of these things really matter. I think slot width is like. Wait, low key. I'm just gonna ask chat. What is min slot width? Chat is like so underrated, guys. Let's see. Oh, okay. I don't really care about that. Oh, right here. This is what I care about. Minimum trace width and spacing is 0.127. So, I think that said also width. Yes. So now I can do here 127 minimum connection width. I'll also do 127. And this just makes sure that I think that's all I care about now. And I will probably close that now. So, let's see, aluminum. Cool. Then I'll open project from template. Oh, I'll probably change that so it doesn't carry over. Oh, you push down on the right side. Yeah. It's kind of sus. Oh, Oliver. Dude, come say hi to the live stream, bro.
Is it a live stream?
I'm live streaming my inverter design.
Oh, that's crazy.
Yeah.
It's like you got like camera and stuff?
Yeah, dude, it's
That's so sick.
Live stream.
Where are you live streaming?
This is YouTube.
That's so sick.
So this is Oliver. He's like Nile Red.
Thank you.
Chemistry.
Thank you. Yeah.
Very goated.
That's crazy. You have viewers? Like how many?
I think I have like, I don't know, 10.
That's crazy. Can you like see their comments?
Well, I have 15 viewers. Oh, there's chat. Oh,
Chat.
they say hello. Oh,
That's
I
so
am
sick.
studying electrical engineering. Oliver's studying chemistry.
Yeah, Kemi.
Yeah.
It's been so fun.
Yeah.
That's so sick. How much of the inverter you got done yet?
Zero. Like,
Just started?
The whole plan was to get it done today, but I have to go ice skating with some friends later.
Have to, you know. I just have to go have fun.
Yeah. Well,
Nice
this
to
is
know.
fun, you know.
That's so sick.
But yeah, so I was setting up some templates, and then
That's so sick.
oh, and then there's also people. I'm in the Discord chat right now as well.
That's so sick. Just got by to grab some parts.
Oh, yo, somebody that got to visit N52, and yeah, so this building is N52. So
Obviously, Miters is like the coolest place in N52.
yeah. Oh,
See you guys.
see you. Yeah, I think somebody was saying something in Discord. Hello. But yeah, if y'all want to join the Discord and like ask questions or stuff, and just like talk, that'd be cool. Usually we have music playing in this place, but I guess that would have been a little too loud. Oliver, what are you working on?
I'm working on, I need like a fan for ventilation thing. I need a blower motor because I need like high static pressure. Overflow.
Nice.
See, something like 3D printed. Should be sick.
Cool.
Is the inverter for,
Sorry, I can like hardly hear you. Let me turn it on.
monowheel?
Yes, it is.
Did you end up getting the JLC PCB?
No, they haven't reached out yet.
Well, you got the CNC one, right?
Yes, yeah, I did.
So sick.
What is it? Oh, I got a message. Yes. Oh, hello. Yeah, I'm just doxing myself right now, but it's okay. Okay. Wait, how long has this been going on for? Does it say? Oh, it's been 38 minutes. Jeez. Holy smokes. Well, yeah. Anyways, I should probably get to designing the actual PCB now. So, make a new project. Oh, okay. So in, let's see. Okay, actually. Okay, so yeah, I just like organize like where my projects are, so it's like easier to see. Let's see, move. Okay. So the way I'm gonna make this inverter is, if you see a lot of like VESCs, which are like open source inverters, it's usually just one PCB, but like the problem with that is cooling. So 12 kilowatts is a lot, and so what I'm gonna have is the aluminum PCB on the bottom with the 6 MOSFETs on it. Actually, low-key, I might just go to 12. I'm not sure. But it has the MOSFETs on it. And then on top of that, I'm going to have the logic stage. And then on top of that, you have all like the bus capacitance. Yeah, sometimes they just do it like this, but that's going to overheat for the amount of power I'm putting through. What am I what? Or sorry, I didn't hear what you said.
What are you doing?
Oh, I'm designing a like a motor controller for my electric vehicle. This guy.
Yeah.
So yeah, that's the plan.
102.
Let's see. Yes, so I'm going to make a new project in, let's see. Okay, cool. Oh, you know what? Oops.
I'm going to let you walk in for a shop.
Hmm?
I want to go now.
Okay. Sounds good. Okay. Let's see, yes. Okay. Wait, well, actually. Okay. Yeah. Running from the template. Okay. Yes, there we go. Okay. Okay. Cool. So now it was over to 6. So now we have our blank schematic for where we're gonna put the FETs down, and I think we can look at the PCB too. Sweet, sweet. Okay, awesome. Yeah. Okay. So the first things first is cool. Yeah, I wonder how many. Oh, Oliver, we have 15 people watching. That's so funny.
That's so sick.
Okay. Yes. So the first thing is looking for the MOSFETs, and so I've already found these ones, and they're low-key pretty cheap. Let's see. It was which one was a good one? Like they're basically like $2 a piece, which is not bad. I'll take that. And because the inverter, you need 6 of them. What is that? $12? I'm really debating if I should put 4 of them. Because if I put 1, like let's say I choose this MOSFET, then 1.1 milliohms at, let's say 120 amps. That's going to be 15 watts. Or it's supposed to be like this. Yeah, so that's like 15 watts, which is, you know, that's actually not that bad. And if you multiply that by 4, yeah, honestly, if I stay below 100 watts on power dissipation on the inverter, I'll be pretty happy. Because really the motor is going to be dissipating like way more than that, and so it's almost insignificant in relation to how hot the motor is going to be getting. I should probably open chat. Oh yes, this is Hyperland. Yes, Motorsports is designing their own custom inverter. Loki, I wish I would have my phone, and I think I am going to record this. I think it is recording, or like stays afterwards. But yeah, like my friend Leon is making a sick FET inverter, and it's I think 25 kilowatts. But the thing is, like, it's different because his is 600 volts at like 15 amps, or like whatever the math comes out there in current. But mine is going to be 65 volts at like 110 amps, or 130. Vestas are pretty good, but why not make your own? You know. Oh, and I'm gonna program all the FOC code in Rust as well. That's the plan. Yeah. Okay, so honestly, I think I'm just gonna stick with these. Theoretically, though, if I was asking ChatGPT about my switching losses, and right now my conduction losses are like, let's say 15 watts, but my switching losses are like 3 watts, which means that if I parallel 2 FETs, I'll roughly I will have my switch conduction losses, but my switching losses, what's the switching loss equation? My switching loss will like about double, because I double the gate charge. Yeah, I mean, well, 12 kilowatts is like totally doable. FOC. Oh, well, I see another one. Yes, I'm gonna use gate drivers, and so the gate I'm probably gonna use like 4 amp gate drivers, because that'll switch the FETs pretty quickly. FOC, I was talking about it a little earlier, but FOC is basically where normal ESCs, they just control these switches blindly, pretty much, just like they just commutate the sequence based on where the rotor position is. But what FOC is that you have these 6 switches, and you actually want to read the current on each A, B, C phase, and you do the math that tells you if you have the currents of here, 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 what vector does that make, and you control the voltages with like a PI loop to where the vector is you control the current vector directly, and because the current is like, well, in an ideal motor, or an ideal like permanent magnet synchronous motor, the vector of the current is exactly where the vector of the magnetic field is, and so if your magnet is perpendicular to it, you'll create maximum torque, and you kind of lead the or like, I guess this way, you basically keep it perpendicular, and then you have like the most efficient drive. But in some motors, there's the optimum angle isn't 90 degrees. It's like, let's say 95, and it's like based on your RPM and stuff. So you have to like, usually you'd want like a dyno. Simple FOC library, because low key is kind of trash. Well, not necessarily, but in any library you use, you basically have overhead. Like VESC has some amount of overhead. Simple FOC has some amount of overhead. And I also want to know how it works, and so I want to write it myself. And I'm also going to write it in Rust. So like I was doing some experimenting with, let me just, I was doing some experimenting with the Rust toolchain, because I'm pretty much moving away from C. C is no longer, like almost all my projects were C, and then now I'm like, the package management is so much better, because CMake and Make kind of just get like annoying. So if I like go to the configuration is like so much nicer, and like the cargo management is just very nice. Yeah, but simple FOC isn't bad. I wouldn't say. But I don't want to use. Well, the other thing is that Simple FOC doesn't have all the things I want, and whenever I want to start adding features of my stuff, then I have to like look at the huge Simple FOC library, which has so much code because it's meant to work with like almost every setup. But then it's harder to program instead of just having like the simple bare whatever I need. Yeah. Okay. Oliver, I don't know if I should use 6 MOSFETs or 12.
12. It's twice as many, right?
Yeah, but that's an extra $6. That's an extra $12.
But like, will it double your power?
It'll increase power significantly.
For $12, I mean, for $12 more dollars. Well, I guess you have to also account for the extra components that you're dropping and stuff, right?
No, it's
it's
basically just you parallel them and connect the gates together.
Yeah, so for $12, you could like.
$12 gives you like
significantly
20-30% more power. Is that
you're
worth
working
it?
like 12 kilowatts, right?
Yeah.
I mean, that's a lot of kilowatts for just $12.
Okay. Well, according to Oliver, I should just parallel 2 of these guys, which is now what I'm gonna do.
Yeah, hell.
Yeah. Let's see here. So, let's open the library and see what we got. What is this package called again? This is called. Okay, well, this is a terrible data sheet. The really good data sheets are made by Infineon, so I'm gonna open the Infineon one. Okay. Okay, it's called toll package. That's very strange. Okay. So toll MOSFET. Okay. Well, we're gonna have to do this one by hand here. Okay. Well, nope, nothing there. Oh, yes. FET, okay. KiCad has a lot of built-in things. You just have to find it. So it's definitely somewhere here. That one looked promising. What does that say? But that's a different package. No. Come on. Okay, that's getting closer. Oh, yes. This looks like the same package, but these are GAN FETs. I mean, I think this is it. Well, it says the package is PGHSOF, which I don't know. Oh yes, perfect. So this is all these power MOSFETs have the same, like literally the same dimensions. So and if they probably have the same pinouts, like it's very probable. I want to see if there's any other ones here real quick. Oh, you know, actually, now that I have that, you can just search for it. So it says HSOF8. Oh, very nice. Oh, sweet. You know, even though these aren't the exact same part, I'm probably just going to yeet one of these. Yeah, we'll just put that on there. Boop. Okay. Also, this is way too big. Okay. Okay. So we're gonna have two of those. Well, actually, in oops. Let's see. When you program the firmware with Rust, it's not the same. It's not the size the files are being. It's not. No, actually, Rust has zero cost abstractions, and so when you compile Rust in C, it's how do you even safety test Inverter? Oh, you don't. Yeah, I mean, you just run it. You just run it. Like, yeah, it'll be fine. It'll be fine. Oh yeah, but whenever you compile Rust in C, it's like it's the same. It gets compiled to the same instructions, and actually, like the Rust libraries that help you interact with the firmware are usually better, even though I'm not using any libraries. But yeah, it actually compiles to like the same. So the main thing of Rust is not that it'll make the program run fast or anything, but it just makes the project management so much easier. Yeah, this is KiCad. And so what I'm actually going to make is a... you can make hierarchical sheets, and so I'm going to call this phase. And so what I can do... yeah, we'll call this like phase 1. Okay. Cool. And so I'm actually going to move these into here. Oh, you know, actually, now that I'm at this, so I want to change the template back to cd dot okay, go in here, go in there, boom, okay, close that, save, and then close that, okay. Cool. Okay. Yeah, I have all my templates in the repository, so that makes it really nice to manage. But what did I do? Oh yeah, I just made the template where this schematic starts at a smaller size, because this is miters. It's a build club, and we have, I guess I'll kind of show it. We have the Doom sled, which is one of the vehicles from the video. We have an electric shopping cart over there. Well, actually, I can. Where's that way down? Oh, look at that. Yes. So that's the electric shopping cart. That's the Doom sled. This down here is the electric trike, and we just like build random stuff, and it's very fun. And procrastinate our homework. Well, thank you. Okay. Cool. So from here, we're basically gonna have two of these in parallel, creating the what they call it a totem pole. And so if I go there, and then, well, actually not quite. So I'm not going to connect the ground just yet. So I'm going to connect that there, and then that there, and there, and then that there. Boom. Okay. So well, it's not technically an output, so we'll put it as passive. And then we'll call this gate low. And then we'll call this one gate high. Oops. And so these are the connections that control the MOSFETs directly. This is KiCad. Yeah. Yes. So the person who built the Cheetah motors was Ben Katz, and we actually have like some of his old stuff here. He was the first one who built the trike. We just refurbished it. He also built like the fastest Rubik's Cube solver, X fastest. Yeah, I use KiCad. This is KiCad. I just have it in dark mode. But yeah. I think a lot of like colleges have maker spaces, which is like really nice. But we definitely have like some lore, which is cool. Yes, we also lean pretty software heavy. The one lab that does like the mini cheetah and the humanoid is like the one lab that's like hardware related, but everything else is like everybody just like doesn't really care much about the hardware anymore, which is kind of cooked in my opinion. But I think it's the coolest thing, and it gives you a lot of like design freedom as well. Yes, so I'm actually gonna go ahead before I connect this to ground or anything. I'm gonna delete those, and I'm gonna place my 3 phases here, and then if I go to my PCB, I can update it, and I get my, oh man, why is that so squished? Oh, it just like broke for some reason. Oh yes, I'm also gonna add a, oh my god. Yes, let's see. Hardware is really cool. No, actually it's not that much math. Like the math that I need to make sure that this doesn't blow up, which is all the heating, is like this stuff, which is nothing more than like some multiplication and divisions. And yes, I used the numbers here are kind of wrong because I know it calculated some of these wrong, but you know it's in the right ballpark, which is good. It's not very much math. It's more of like knowing what numbers matter and like multiplying and dividing the right numbers to get you like how much power is it going to dissipate. Yes, it is KiCad. Dude, C++, bro. Oh my god, no. Dude, some guy came in and his thing is C++. I use C, or now Rust, but I was never a fan of C++ low-key.
I disagree.
Yeah. Oh, dude, we got 20 viewers now.
Hey.
That's crazy. Yes. Oh, yes. So I need to measure the current somehow, and there's like a lot of ways to do this kind of, but yeah, the best way, well, there's 2 options. I'm just gonna put a resistor here. So option 1 is to, let me get ground. So this is option 1, is I put my shunt below, this keeps tripping me up because I have 2 in parallel, so I keep thinking it's a half bridge, but it's not a half bridge. Or it is a half bridge, it's not an H bridge. I don't know what I'm talking about, but anyways, but you can either put the shunt below, or you can put this guy in front of this, like so. And there's 2, I guess it kind of varies on like, oh no, that's not good if it exploded. Yeah, I've seen tiny tape out. You can actually learn a lot in a year about electronics, especially if you like grind the YouTube videos. Well, I like learning through YouTube, but and so I grind YouTube videos sometimes about learning about things, but not really grind, but like I want to do a project and I know I need to learn like XYZ as I'm going along, and so I watch the videos on that, and so I kind of like learn what I need to get my project to work. Oh yeah, Tiny Tape Out does like some ASIC things, or like, yeah, you can make your own ASIC, and it's like not too expensive, which is cool. Oh yes, so there's low side sensing or there's phase sensing, and the thing is like they're both like nice in their own ways, but I think I'm leaning towards low side sensing, because high side sensing you need like really fancy differential op amps that can withstand, because the voltage on this wire goes up and down like by like 80 volts, and so it's like constantly going up and down at like 25 kilohertz. So you need some like crazy common node rejection on the differential op amp reading the voltage over the resistor, and it's just like cooked. Oh yes, RISC-V would be fire. I don't know how big it would be and if it would fit in one of the things they give you, but it would definitely be really cool. Oh yeah, I don't have a job. I am jobless right now. I'm just I'm at school. Oh yes, electronics is actually in like super demand right now. Like I hear this from my friends in like Boston Dynamics. I have some friends in Tesla and like all these companies, SpaceX. Oh, MIT is like a school over in Boston. But yeah, electronics is in like pretty good need right now. Oh no, you do not need to understand the physics. Like I've just started to understand the physics, but like it's not important. The mathematical equations, that's also not important. Like for the stuff I'm doing and a lot of power stuff, you actually don't need to understand gain or any of that, because you're just switching the MOSFETs. They're just turning on and off, and so you can just characterize them as like switched on or switched off, and like the equations of how they switch on and how they switch off does not does not matter. Yeah, no, yes, I do use Linux. I'm on an Arch right now, and I'm surprised the streaming is working. So, yes, this is a makerspace we have in MIT. It's like right next to the motorsports. So, yeah. Let's see who's popping. Okay. Wait, no. I'm gonna go back here. Yes. Yes. So this, I'm making an inverter, which I think I can just, yes, I can move that over. So I'm making an inverter which has 3 phases. Here I have an extra double set, but I'm going to explain this really quickly again. You have switches, and you control these switches in a certain way to control the motor and give it, like, make sure it has the right output torque you want. And so I have this like really chunky 12 kilowatt motor that I want to make a motor controller for, and these are the power switches for it. Oh yes, Claudius, and I do know Claudius and Monica. I'm good friends with, well, I see Claudius pretty often. No, I do not play on, I don't really play video games this day and age. I'm studying electrical engineering. Oh, I'm running Hyperland on, by the way, yes. Yeah, I don't know if you met KG too. KG is like good friends with Claudius. But yeah, I mean, Claudius and Monica aren't on the team anymore because they're seniors, and so they, what do you call it? They, like, the seniors don't, like, kind of leave the team and try to, like, pass the information down. It's like, so the sophomores and the juniors get to do more. It is a small world. No, it's not much math. It's really not that bad at math. It's just like understanding what math you need to do. And then once you kind of do it enough, you don't really do the math. You're just like, that number seems right, you know, just by like vibes. A lot of it becomes vibes. For example, I'm going to ask. No, actually, it's not an H bridge. So this was tripping me out too earlier. But for my inverter, I am putting 2 FETs in parallel because I'm running 150 amps through it, and you can only get like 1 milliohm FETs. And so I have 2 in parallel, so I have half the resistance and half of the conduction losses. Because I can afford more switching losses. Because if you put 2 in parallel with the same gate drive, they switch slower, but that's okay. Yeah, that's fine. Alright, see you, Lucas. Ciao. Do you think Comp E is relevant? It's... No, I'm not really doing any programming. This is like the schematic layout of the inverter and like the electrical design. I think is like Comp E like computer science and electrical. I think both are relevant. Like a robot, you need literally everything. You need the electronics and the firmware. So it's like it can't work with either. It just depends on like who's doing what. Yeah. Yeah, so this is just 1/2 bridge, and so I have 3 of these, and it's like an H bridge with a 3rd leg, and so I have 12 MOSFETs, and I'm gonna start laying it out soon. I was gonna find, so let's ask chat, what is a good shunt value for? Okay, see, this is how you oh no, so this is or if you're asking if this is not the logic stage, this is the power stage, but of the controller. But later you do need the logic to control the switches. Okay, so it's telling me that 0.8 ohms is the sweet spot. Well, if I have 1 ohm, or 1 milliohm, and I have 130 amps, that is That is 17 watts. Yeah, so we're gonna need some fancy shunt resistors. Let's see. Let's see who's watching. We got 15 people watching. Very cool. Okay. Oh, yeah. So, like, we have some classes in MIT, which is just like run by students. And so now I'm like managing that class, even though like I'm kind of procrastinating managing the stuff. But yeah, so like it's just like students run it, and now I'm running it for the next class year of students, and it kind of just gets passed down over time. It's like a class, but almost feels like a club. In the way that like it's run by students, and this makerspace is also student run. So like we have like some lathes and mills in the back, and you just get trained by the upperclassmen, and then you just like kind of pass it down. It's pretty cool. Oh, my friend's like over there. Yeah, it is pretty cool. It's not quite a TA, because the class isn't really for a grade. It's just like a fun thing to do over like the January period. So, yeah. Let's see. So now we're gonna do some more shopping. So I'm gonna actually keep that tab open, and I'm gonna open a new tab, and I'll just do open that. So now we're gonna go shopping for some resistors. Yeah. So shunt resistors. In stock. Oh, I'm making an inverter. So, like, this is my electric vehicle that I'm putting together, and this is the motor, which is actually this guy right here. And I need to make a motor controller for it. So it'll take, this is the blue, the battery is this blue box, and so it basically converts the DC to the AC to control like the speed and the torque of the motor. Yeah. Ooh, wow, this is gonna be rough, because the resistor is gonna have to. Oh, I'm using FreeCAD. It's like open source CAD software. So like instead of like Onshape or SolidWorks. Where did I get the inspo? I don't know. I just saw it. Oh yeah, I do know about NAN. I don't use it personally. But apparently you can do some very nice integration with that stuff. But the thing though is they have a really weird model where it's like you can get the source code on GitHub, but it's not open source. Like you can't use their software freely, which is kind of like I understand they want to make money, but it's strange. Okay, so let's filter here for There's no other way to do this besides just clicking everything. I wish JLC had a little bit of a better search tool. Oh no, dude! If you're 15, you're still a kid, you know. Like, you're totally fine. I wouldn't say I'm like a genius, but I'd say I'm quite smart. Plasticity. Oh, it's like a modeling software. Oh, see. Well, okay. The problem with stuff like this, Parasolid, or I think, what is on-chip run on? Yeah, like everything uses the Parasolid kernel, and like sure it's really good, but like that means you have to charge like a pretty significant baseline amount of like cost for the software. And like sure what FreeCAD uses is Open Cascade in the background, but it works, and which makes it Open Cascade is also open source, so it's free. Are you charged? No, it's all free. Like all the student resources at MIT are just free. I mean, yeah. I do not pay for ChatGPT. I just use a free version. And when I run out, I go to Claude. And when I run out, I go to Grok. I study electrical engineering. No, but like paying for anything is just like not real. I would not pay for software, because like there's so many free and open source things that I can just use that work. And you can also contribute back to them, or like if you want some feature, you can just edit the source code and recompile it. So
I'm headed out. Bye, chat.
Oh yeah, that's Oliver.
Always wanted to say chat.
Oh, no, I don't use Windows anymore because I think it's garbage. So I use Linux and all the Linux and open source ecosystem, and it's great. Yeah, pretty much everything that runs on my computer is open source, which I think is like better for the world too, in general. Alright, ciao. Leave life. Oh yeah, I'll probably leave it. Yeah. I'm running Arch, and the window manager is Hyperland. Yeah. Okay, so I'm gonna see if I can log back into making this inverter. So yes, the 12 kilowatt inverter. Here we go. What was I looking into? Oh, I was looking at the resistors. Yes. So I have to find a really chunky resistor. Oh, like something like this. That's kind of what I'm looking for. The only problem about something like this is it looks like it's made out of copper. And if it's made, oh, actually here it tells you. If it's made out of copper materials, copper has a pretty high temperature drift, which means, oh yeah. I mean, actually, there's like Libre something, which is like all the Microsoft tools, but like open source. Oh yes, FreeCAD is definitely a serious alternative. Like, I think the thing is like software support is great for the software that's like supposed to, like, sure, But yeah, I actually have my computer dual booted right now to Ubuntu, Windows, and Arch, but I don't really use the other ones. The thing is, like, the software support for, let's say, something like the Windows ecosystem stuff, like some like Microsoft Windows won't run on Linux, but there's equivalents of like everything that are open source, and so like all the software that's open source runs great on Linux. So FreeCAD runs great on Linux. KiCad runs great on Linux. And like all the software that's meant to run on Linux runs well. And like all the stuff you need. Like sure, maybe Adobe doesn't run well on Linux, but I use like Kdenlive, which is like a open source editor. So there's like programs for everything that run on Linux, actually. It's a misconception, I say. Yeah, the first 2 years, okay, that's fair. I don't think Adobe's a good company. 'Cause they charge you like an unsubscription fee. I saw PewDiePie's video. Like that's crazy. But WSL and Windows is like a good combo, I'd say, if you like the Windows. Like you got to give props though for Windows being so backwards compatible, but yeah. But the thing is, like pirated software, you don't have the source code. Like what if well, I guess for editing software you don't care, but like for FreeCAD, I want to like do my own integration with stuff, and so that I can never do that with SolidWorks really. Like if I want to recompile the source code for some features I want. Yeah, actually, whenever I move to stuff, I'm going to. Oh, about like learning math and stuff, like yeah, I spent the first year and a half like here, like doing all my math classes and headers and that. Yes, I think you can build a robot. You just like you can figure it out. I think the biggest thing is being curious and driven to want to do it, for sure. What else was I saying earlier? I forgot. Oh yeah, there's this thing called truck, which is so like Parasolid and Open Cascade are the kernels that do the geometry intense math, and like they do the Boolean operations and figure out what all the equations are that constrain everything. And the cool thing is these people have, I think they're like Japanese. They made this open source thing that runs on web GPU and Rust, and so this is like the coolest thing ever. And so whenever I'm making like my own CAM software for my CNC machines in the future, it's like you can basically CAD in just by coding. It's like you can directly like program the kernel to do stuff, which is pretty cool. And like, oh yes, like they did an example of like how you would model this with like some code. It's very, very interesting. I'm 20. Oh, I mean, yeah, I think the whole point of lectures is to learn. It's also nice to interact with, like, here, like, if you go to class, like, a lot of your friends go to class, and so, like, you get to talk about cool things in class as well. But, I mean, sometimes I don't go to class. It really depends on your situation, if you think it's worth it or not. Okay. Let's see. So if I go back to here, it's ASR K7. Oh, wow. What is the resistance? 1 milliohm? Oh, what size is this? 5930. Okay, so K. Oh, that's actually really good. So if you look at the drift, it's 50 ppm per C, which means that let's say my inverter gets to like 100 degrees C. How much? Let's see. See, I don't even have to do the math. I can get ChatGPT to do the math for me. Let's see. Okay, that's not bad. That's 0.3% over my full temperature range, which means that these are actually pretty good shunt resistors. They'll work pretty good. The only thing is that they're rated for 9 watts, which means that if I put 2 of them, I think if I put 2 of them together, it'll be okay. Let's see. If I have half a mil, let's see. Times 130 times 130. So that's 8.4 watts. Wait, really? Oh yes, so if I have one of these, it's going to dissipate 22 watts, which is way too much. But if I have half, then the total dissipation is 11, which if you divide that by the 2 shunts, that's totally okay. Yeah. Very nice. Do you want to own a company in the future? I do want to try to start a company in manufacturing, like robots and stuff, or just like manufacturing, and then probably build stuff like robots with my stuff. I mean, I always found physics pretty. It was like pretty intuitive for me, but a lot of like the electrical engineering stuff that like wasn't taught in high school, and that I didn't take any classes over. I just watched YouTube videos and stuff. But for electrical engineering, a lot of it you don't even need physics, and you don't really need any math besides like basic algebra, which is pretty cool. It's more of like a building skill and less of like a like the theoretical skill, I'd say. Oh, okay, cool. So this is actually great because I have an aluminum PCB, and so it'll be able to pull. Use integration for game theory. I honestly don't even know what game theory. Like, I think you're talking about op amps, but I never use that stuff. Well, I mean, for the current sense op amps, I will need to use a little bit of that, but I mean that's like it's pretty niche usually. No, I'm not very tired. I'm just I mean I'm pretty much here for like all day anyways, just like working, so I think I am going ice skating with friends like at 8 p.m. or something, but no, I mean like you don't need to know any chemistry, you don't need to know any like what else do you have? I mean you gotta know that like 60 degrees Celsius is like really hot and you'll burn yourself, but like I mean you get a little bit of intuition on temperatures because a lot of power limitations are based off temperatures, but like just knowing that all my circuitry should be below 100 degrees Celsius, that type of thing, and like whenever I'm looking at this data sheet, it's telling me like just some temperatures and just like reading graphs a lot of the time of like, is this okay? And it is. So let's see here. I'm thinking about putting two of these in parallel, but that might not be a very good idea. Well, it's saying that that's kind of sus, but you know what? It needs to use the ID. There's some videos online, like that get you started with the STM ID pretty well. But low key, I think sure, the ID is still super common right now, and I used to use it. But I've moved over to using Rust completely, and I don't have to use ID anymore, and all the configuration is done with like cargo and like in the program. I'd probably say somebody like deleted all their comments. Huh, interesting. But yeah, I would say like if you know. It depends on if you want what you think is the future, or if you want to have a skill for like that might be used more frequently in a job. But like all the robotics companies are like moving to Rust, especially the new ones. So yeah, I think Rust firmware is the future of like that type of thing. So it's also easier. It's so much easier to use Rust than like the whole STMID thing. It's kind of new-ish in the past few years, so there's you have to like look at the documentation more, but the documentation and the tutorials on like the Rust official docs are pretty good, and that's how I was getting started a few days ago with. So I'm actually just gonna put one of these down. What size was it? 5930. And okay, I don't know why it always does that. 930. Well, the resistors don't even get that big, so that's okay. What is that gonna be? 56? Okay, it's about this. Yeah. Okay. So I'm gonna do that, and move this back over. Okay. Okay, so the actual ones are gonna be about double the length of that and about double the width, which is pretty chunky. Yeah, that's pretty big. Dang. Well, I feel like it's not the end of the world if I put 2. Well, anyway, let's see. Let's see. So, if I have this, so these are my first. This is my first totem pole here, and how many people are still watching? Oh, we got a few. Hello, everybody. Yeah, so we have these 2 bottom fits, and I want them next to each other for first of all. Yeah. So I'll put them. Oh, why they grab at different spots? Oh, there we go. Well, I guess they don't want to be in the same spot, but different stuff you learn. Well, that's the thing. I don't learn things I don't find interesting. I cannot remember them. So if you ask me about biology or any history, I don't know. Don't ask me about where countries are in Europe, because I probably don't know that either. I just somehow remember all the stuff that's related to electronics. I don't even remember what day like Easter is, or like I forgot like when Christmas was not too long ago. That was pretty funny. I was like, I didn't know if it was like the 24th or the 25th, like which one was Christmas Day. Like anything that's I'm making an inverter for my big electric motor. Yeah, so yeah, well that's tough. Yeah, I'm lucky in that I find it interesting, so it just like sticks in my brain, which is very nice. Okay. So, see, what I'm thinking is that I can't make it where they all come, the buses all at one side, because then my inverter is going to be super long. And so what I'm thinking right now is if I put like the plus side on the right and then the minus side on the left, so like imagine like that's rotated a little bit, then all the power is like right here, so like this all connects together. Oh, actually no, that needs to be rotated, so like this all connects together, you can see. The only weird thing, well, no, that's not that weird. And then Yeah. Yeah, I think that's just a much better layout, not gonna lie. Yeah, it is like Flow 360, and you kind of just have to figure out where, like, what is the most optimal layout. And honestly, like, CAD is the same thing. Like, I was banging my head against the table so many hours trying to figure out how am I going to make this, and then I finally kind of converged on how, like, it's going to be made out of sheet metal and stuff. Yeah. So, like, the one main bus is going to be here, and I think the other one's going to be here. And you know what? I think if I put... Well... Oh, dang. See, I want to use two really big shunt resistors that are about that big. But the problem is that if it's half an ohm, I don't know if I don't know if I'll be able to read it or not. Because what is 0.5 times 100? What is 5 watts at 100? It's 10 watts. That's not bad. But the thing is that, like, 10 amps, that's 5 millivolts. That's really small. Well, let's see, 130 times 2.5. It's gonna be 65 millivolts. That's on the low side, is the thing. So it's like a trade-off between just like over time with like YouTube videos, learn like what all this stuff does. Yeah, it does take some time to learn a lot, but then you kind of just like vibe things together. Yeah, this is not looking too happy, because it's saying that, okay, well, first of all, if I want 12 kilowatts, right? So if I take 1200 and I divide that by 65, that's 180? Okay, well, that's ridiculous. So 180 times 0.5? Yeah, this is kind of crazy. Well, oh, let's see. Oh, yeah. I do my homework beforehand. Instrumentation amplifier, I'm not exactly sure if that's what it's called. What I'm using is like a diff amp, so it's like differential reading on the resistor. Oh, yeah, I can answer anybody's questions. That could just hamper your flow. Oh, yeah, like, I'm not getting very much work done right now, but I thought it'd be interesting to make a stream, because why not, and see how it turned out. What channels do you recommend for it? I mean, really, there's all types of channels. You just have to search up whatever you're looking for, and it'll probably be there. You just have to find what you're wanting to learn, and it'll pop up. OS underscore? What is that OS? I'm running Arch Linux with Hyperland as the window manager, and then I have like a way bar set up here, with some stuff. Let's see. Let's see what ChatGPT says. Huh. Okay, I think I'm probably. Do you have any book recommendations for building a strong math? If you only choose between, I would choose C. Definitely C, because C++ just does some abstractions like classes that you have no idea how it correlates to the actual assembly. And C is like super direct. Like you don't have classes, you have structs and pointers that are in the structs, and that basically represents your class. Book recommendations? No, I don't have any book recommendations because I don't read books. Because I just can't sit down and read a book. I'd rather like watch something or like read an article or something like that, like a blog post. But there definitely are some that you can find, like if you search up like what other people think are good book recommendations if you like reading books. Okay. It looks like that's the plan. I've chosen that I'm going to use two half a milliohm. 0. Okay. 2 half milliohm resistors for sensing here, because anything higher yeah, there's definitely a bunch of good books for sure though if you're into the books route. Okay, yes, cool. Okay, so I'm gonna go with two 1 milliohm. And so these two, like this is like some math that is sometimes common. It's like if you have two of these in parallel, you divide by 2 and it's half of that, so it's half a milliohm. And that'll be about good power loss. But like it's a balance of, if you increase the resistance, you lose more energy to it, but you're able to read it better, and vice versa. The other way is like, yeah, you can't read it as good, but you're not losing as much power. But the thing is, I can't find, I don't think I could find a, this is like really big already. I mean, I guess they have bigger ones. Like this isn't even a resistor, it's just a chunk of aluminum or something. Oh, here's another one. Half a milliohm. Well, the other thing is that if I hit my 180 amp peak, then I'm hitting 16 watts of dissipation, which is kind of high. Well, you know what, actually, if you look at like the CAD, it was just because I found that part, and it seemed easier to use too, but I'm low-key recollecting on it, and the thing of this vehicle is that you can only accelerate as fast as you won't start rotating in it. And I am going to have these, let me show these weights. These are just like big chunks of steel, these like blocks right here. And what they do is they just counteract your mass. So these blocks will like move forward when you accelerate, and they'll move backward when you decelerate. And I'll probably make them even heavier. So, but the thing is that determines your maximum acceleration, and low-key, this motor is just gonna like, it's just gonna be too powerful, you know. So, are you designing power stage now? Yeah, I am designing it all. Like I'm designing the power stage right now, and then I'm gonna do the control stage, and I'm writing all the FOC firmware in Rust. And all the firmware running on all of it. I'm also going to design. Yeah, it's totally possible. Most people, they just buy a VESC, but I think it's cool to design my own, because I really want to get like some good motor control stuff going on. Because yeah, I mean, it's just like nice to have. Oh man, I'm thinking about it, and I'm really tempted. Why Rust and not C++? What a pendulum's from turning into a vertical merry-go-round. Yeah, that's basically what I have. The pendulum system is that mass. It moves back and forth, but it's driven by a motor, so it's like actively. There's going to be a gyroscope on one of the control boards, and it like actively compensates to keep you as flat as possible. Why Rust and not C++? It's because Rust is just so much easier. Not the language itself is kind of arbitrary. Like, sure, it's safe, but it's not necessarily why I'm using Rust. It's because like the cargo and the library management and the stuff I've had to do with C make is just such a pain. And with Rust, it's just like cargo, and I can make my own libraries that link way easier instead of having to edit the make file or the C make files. It's just less of a pain. And yeah, and because like I'm also gonna be writing like software in Rust, because I think I also like the efficiency of C, and it's like Rust is the only, well, I guess there's Zig, but Rust is like the only language that's like good package manager that feels like pip, that is, you know, like you don't have a lot of overhead. Yes, third-party packages are so painful. Oh my god. What speed are we hoping to get out of it? I think, my friends tell me that I'm gonna kill myself somehow, but I don't think it's gonna happen. This is gonna be so safe. And it's gonna go at least 60 miles an hour, and the speed record for a monowheel is like 90 miles an hour, so I think I can low-key hit that, because my friend had a scooter that went 90 miles an hour that he built. So I think I can do it. Guinness World Record, it's gonna happen. Okay. Yeah, but you know what? I don't know how much I should aim for on the. Yeah, I don't know if I should go 1 milliohm or half a milliohm. What's the CAD software? FreeCAD. Can you run simulations in it? Yeah. Well, okay. I was trying to get CFD working the other day, but I didn't get around to that. There's FluidX3D, which doesn't run in KiCad. It's just its own like C scripts. It's just like some like 10C files, and you compile it and you run CFD on that. But yeah, let me see. I have this part here, these hinges made out of aluminum. I did some FEA on it, and I have like really good safety factor actually. So I was just like, oh, I want to do FEA. So came out nice. Are you going to throttle control with pedals, or are they just serving a footrest? Actually, I haven't decided on this. For maybe foot pedals. I think this is like a final option thing of like, I'll build it and then maybe try both, but because your hands are on the steering wheel, it's like, should you have paddles? I don't know, but I think it might be pedals. I'm leaning towards pedals. Time management. I mean, I think my time management isn't great, honestly. It's just that I spend like almost all my time doing this stuff. So even if I'm like not that time efficient, it's just I still have just like most of my time designing stuff. And you know what? I think I have decided that I'm gonna go with a 1 milliohm shunt. Because, yeah, if I go with half a milliohm, it's just really low signal to read, and there's so much noise because like all the switching, you're switching like a lot of. Well, I guess the voltage you're switching is not that high, but it's still significant. Won't it be turning like a motorcycle? Yeah, a motorcycle has a steering wheel. This is KiCad. Well, okay, a motorcycle doesn't have a steering wheel, but it has steering handles. So like in I guess in a bike, it's just like the steering wheel's like angled down, but the steering wheel here, it pivots this like tire part from this like internal frame that has the seat connected to it, and that's what these hinges are for. So these hinges connect between the bottom frame and this like tube frame here and here, and they let you kind of the wheel and you lean separately, and so that's what gives you the stabilization. Well, I just didn't do half of my homework last week. C's to get degrees. How will your head body be protected? Helmet, gloves, shoulder pads, and knee pads when I first test it. Yeah, well, handlebars also are steering, so it's like the same thing, right? Like you have something that moves. It's not like fixed. So that's what makes it stable. I mean, so imagine if you took a bicycle and replaced the handlebars with a steering wheel, you'd still ride your bicycle. It would just be like slightly different. Also, based on the seating position, it's just more ergonomic to have a steering wheel. What size motor do you have to estimate for the lift for it? Oh, so this is my motor. The motor is like 10 kilowatts. There's no labeling on it because I just found this. But my friends say it's like 10 to 12, so somewhere around there. How's it going to turn? Oh, the steering wheel. and the steering wheel leans the tire. And then you also have a flywheel that helps keep your inertia this way high, so you don't fall over. Okay, let's see. Oh, oops, no, I didn't mean that. 1 milliohm. Oh, okay. Well, actually, one of the greatest things is, instead of doing the math, will it change direction? Oh, yeah, so whenever you turn the steering wheel, the wheel leans to the left. And because the flywheel internally is also spinning this way, there's going to be a weight shift, and just how like a bicycle starts leaning, it'll also turn, like so. Add code. Canvas. Oh, very nice. Any tips, because the whole thing is kind of over. Oh, well, actually, for this project, I'm making my BMS as well, but I'm making it. Are you Portuguese? No. Both my parents are from Mexico. Yeah, I'm making a custom BMS, but I'm not using a BMS chip. It's like all analog, so like just a ton of transistors. Well, it does have an STM, but everything else is like just like the STM talking to on all the analog part, which is like kind of funny. But I wanted to like learn how the BMS chips work internally. I'd say use like the TI BMS chips. Like there's this good one that I was going to use. Man, they have these nice. It also depends on how many. I assume you are using like modules. Oh yeah. Raspberry Pi's kind of sus, because usually BMS stuff is just like the STM directly. I use KiCad for PCB design. Oh yeah, these BQ BMS chips, you can find them that they do the 16 cell ones, and they have analog channels, and they can communicate directly with like SPI, and they're just really nice. And so using one of these guys, it just does everything you need, all in one. Pretty much, it's very nice. So if I was smart, I'd be using that, but I'm not. Well, because I want to learn how to do it myself. I always do things sometimes for unreasonable reasons, but I think it's cool. Okay, what is... Well, actually, let's see. What is... Okay. Interesting. So what a lot of people are saying on the internet is that usually I'm 20. Yeah, STM. Oh, I see. Oh, okay. So the Raspberry Pi is like reading the CAN bus. Yeah. Yeah. On my repo, I have some stuff about. I was trying to test out CAN-FD. It came out nice, but I don't know if the Raspberry Pi stuff supports CAN-FD. But you do get faster data rates if you need it. But I would have crashed out. Oh, if I was any younger. Oh, yeah. No, yeah. Oh, I didn't realize it said 20. Oh, in chat. I'm dumb. Yeah. I mean, I think it's just keeping the design as minimal. It's like feature creep always comes in, and so like for my stuff, I'm like, what is the minimal stuff I need, and that's it. Because sometimes these chips have so many features, and you want to implement them all in the circuitry, and then it just comes back to bite you. Okay, yeah, a lot of people are saying online that about 100 millivolts is as high as the shunt voltage gets. So like here he's talking about okay, let's see here. Yeah, so people are saying usually don't go above 100. So yeah, actually I am gonna stick with the half a mil ohm. And yeah, the other reason I'm using 2 is because it just packages better, and I could find the part that does, and the heat dissipation is also better because they're like separate. So this is actually going to work very nicely. I'm happy I figured that out. Cool. Let's see who's still watching. Oh, we got a lot of viewers. That's very cool. Thanks for showing up, guys. Yes. Okay. So now, I need to get a proper footprint for this, because this was the yeah, because you're not gonna find a shunt that does 16 watts realistically. Like that's 9 watts. Also 9 watts. Wait, how does it do 9? Oh wow. 8 watts. Oh wow, this is cool. So this is like a small shunt, but it does 8 watts. Wow. So 3920? Wait, where? I keep forgetting which window is what. Okay. Wait, what size is even coming, KiCad? Oh, it's basically this size. Okay. Okay, so I fixed that, and I should be able to refresh this. Oh, sweet. Okay, so this means that oh no, it'll probably look something like that. Yeah, and then the cool thing about doing it like hierarchical schematics is that you can use this replicate. Oh, it's fine. Oh, so yeah, you click on that, and then boom. Oh, oops. Wait, I need to go to here, and then click on this guy and put that guy right there, and then here, and then put that guy right there. And then if I click here, and I go there, oh, right there, boom. And then this is probably what I'm going to do the layout in. Hello. So I'm thinking, yeah, this is actually looking very promising. Yeah, I like this layout, and the phase wires, Yeah, so the plus bus is going to come from the left, and the minus bus is going to come from the right. And then the phase wires are basically just going to be, let me see if I can find a pad. They're basically just going to be like pads. So that's like A, and that's going to be B, and that's going to be C. And then you have your 3 really big wires coming out of here. And yeah, I think that's actually going to work great. Sweet. And then yeah, because this is mounted on an aluminum PCB, the heatsink is on the bottom. Yeah. And then actually I can open it up in here. So this is kind of what it looks like so far. You have like the big FETs, and yeah, sometimes you can get MOSFETs with topside cooling, and they're like significantly more expensive though. And so yeah, if I make this with, oh, I didn't edit the board thickness properly, so it looks funky. But yeah, if I change this to like silver, it'll look more normal. Oh, that's not the right color. Oh, I see. Something like that. Yeah, so this is what the PCBs can look like, to some extent. And yeah, hopefully it doesn't explode. Make a keyboard. I actually thought about making a keyboard once, and I made like a it was just like a few button keyboard. Let me see if I can find it. If I go to repositories, I think it's one of these. Yeah, I have like so many random things that I. Okay. Well, I really thought it was in one of these, but I don't think it's actually here. Switch panel? External USB switches with... Oh, I think it is this. Oh, yes. Is it this? Well, I think I did make it. It was just like a little keyboard, but it had like 4 keys on it. Any good projects with electrical engineering? Usually it's stuff with like Arduino, and I think it was a good way to start. And let's see, one of the first things I did was I'm not sure. I don't really remember. Really just whatever you find interesting, like some small thing that solves a problem that you have, like, oh, what if I want to make my blinds on my room like open when I clap my hands, and like you figure out how to get the motor to like some mechanism that spools up something, and then like you get the Arduino with like a microphone and it'll sense the clap and stuff like that. Like it doesn't have to be super complicated. Oh, why triple boot and why Linux? Ignore the well, I actually don't even use the other two anymore. Oh, my dad's watching. That's funny. That's my dad's YouTube account. That's actually really funny. Why triple boot? Well, because at first when I installed Windows and I was moving to Ubuntu, I was like, oh, I don't want to delete my Windows, and so I kept it. And so it's just because I want to keep stuff. But I think eventually I'll clean out all the files and just have Arch and probably Ubuntu, because stuff like there's some things that only run on Ubuntu that don't run on. And actually, every now and then you need to use like some other software. So not on my computer, but on my laptop is okay. That's so funny. I wonder if my dad texted me. No. Oh. Yes. So the other thing here is that on top of this is going to be the logic stage. And so these are all the switches, and the power goes through here. But the control, there's not enough routing, because this is only a one-layer PCB out of aluminum. And so the top, on top of this is a four-layer PCB, which has like the stuff that controls all this, the mid-power stuff. And I need to figure out how, because if you look at these, like I'm pretty sure this pin, these two pins, or this pin is like the gate, and so this pin needs to go up to the next circuit board on top, and so does this pin, and so all these pins need to somehow connect back to the top. So this is the gate, and the gate needs to connect back to the top. And so somehow I need connectors to do so. Another thing is that all the because it's an aluminum PCB, and I'm mounting the heatsink on the bottom, I'm probably gonna make it where the power wires go up, like up through the yes. So they're gonna go up through the power stage board. Oh yeah. Yeah, the car was like my dad's passion project, and I just got to help a lot with it. It was really fun. And yeah, I mean, it broke down a bunch of times, but it's working pretty good now. Minimal problems. And my dad likes taking it to car shows and stuff. Oh, like on the Discord bot? I don't know. What, Oh, that's true. I don't know how to set commands. That'd be interesting. Yeah, that'd be pretty cool. I might set that up. With like one of the Discord bots. Oh, and I did mess around with making some Discord bots back in the day. But I never touched it again. Okay. I also think that if you look at like the VESC schematics for like the VESC 7, they use an unbelievably small shunt resistor. Which you would think, how do you even read the current on that? Oh well, no, never mind. It is half an ohm. But let's see what FETs they're using. Well, I can't even highlight it. It's not wanting to. Oh, there we go. Yeah, a great way to, like, instead of having to design everything yourself, you kind of look at what other people did, and then you get like a good reference point. what's FOC? Oh, FOC is like where you control the currents through the motor, so you get like the right magnetic fields that kind of push on the magnet, like the effective like magnetic pole of the motor. Yeah, so actually looking at this package for the VESC, they have 1 milli-ohm FETs and the shunt resistance is half. So the fact that I have where am I? Okay. The fact that I have, let's say, what is this going to be? Half? No, 0.7, and using 1 or half is like really chill. Yeah. Yeah, that's totally fine. Wait, is it? Yes, yes it is. So yeah, I'm gonna keep the 1 milliohm here, and so this, yeah, actually with this stuff, yeah, I think I'll be able to hit like 12 kilowatts for sure. And so maybe not like mechanically hit 12 kilowatts, but like I might make a dyno with like these inverters and the motors, and this is gonna be a really nice inverter to have in the future. Yeah, so what next? Yeah, I'm not really sure what to do now. Oh, totally lost. Well, I'm trying to explain. These are the switches. These switches. Well, okay. So I have this motor, this very big motor, and you need to make the electronics to drive it. And so you have 3 groups of switches which connect to the 3 phase wires of the motor, and they that's how you drive it. And so this can do like 150 amps continuous, and it's just mounted on like an aluminum block, or like the circuit board is also made out of aluminum for like heat transfer. Okay. Yeah, I'm not sure. Well, now that I know the rough form factor, that because these are going to be here, and then if I just get like a okay, let's like pretend that this is the plus bus bar. Okay, so let's pretend that's there, and let's pretend that's like there. So it's kind of going to be a square. We'll move it over a little bit. But yeah, so the inverter is going to be a bit of a square. And usually when like designing stuff, it's really hard to converge on a design for one part and just solidify it and then go to the next. It's very like do it at the same time. So what I'm gonna do is I'm gonna close. I don't think I need this. Well, actually, so we're gonna make the drive stage now. It's also the logic. Well, actually, there's also the capacitors, but I think that'll fit in the drive stage. So, I'm gonna make a new project. So drive stage, cool. And we're just gonna call this drive as well. Sweet. So I'm gonna put this in 7. Okay. Maybe I had questions. Oh no. Wait, of course. There's still people here? Oh, there is still people. Hello. So yeah, I don't need to worry about the VESC anymore. Yeah, so this gives me pretty good hope that I'm on the right track, because I'm referencing this and my values are way more conservative than what these guys do. Very nice. So now we're on to the drive logic. And oh, you know what I didn't do? Oh, I messed up. What I meant to do is okay. Yes. I meant to make it from a template. And so I'm gonna select the 4-layer board template that I made. Yeah, because I think the drive circuit will also be 4 layers, or will be 4 layers, as well as the logic. So we're gonna call this drive and save. Cool. Okay, so now it's template, the template that I have. And the template just has all the PCB like fab requirements and stuff like that. Why do people use Linux? Because it has stuff that's it's just like you can the computer does what you want it to, and like sure sometimes the configuration is FOMO? What? No, I don't think so. The computer does what you want it to, and like you learn how the computer works. Like if back when I was using Windows, like I didn't understand how a computer works, and like Windows is basically like magic, and if something breaks you can't fix it. Like if you get a Windows error, you're done for. In Linux it's like, did I refresh in the package down there? Oh, well that's really cooked. Yeah. I hope you got the LTS kernel as a backup. How do you say what projects to do? I don't know, just whatever I think is my like interest, I'd say. I think this is cool, and then I work on it. Yeah, I don't know why KiCad. Well, if it's a black screen, it like what window manager do you use? Because I remember I installed some X11 packages for like X Wayland to run some stuff, and it just destroyed my Hyperland. But you can press like Alt something and you get into a terminal and you can fix things from there. Oh. Yeah, that's very strange. Yeah, go into the TTY1 and see if oh, okay, nice, yeah. I remember I was stuck for a few hours fixing things, and I realized, well, I was compiling some CFD software, and I went into like the /user like include and started editing a bunch of include files that are managed by Pacman, and that was like not a good idea, and I learned that now, but that's okay. Yeah, with Linux you kind of figure out as you go, or like you get to learn how things work, which is cool because then you can make your own things. Yeah. Okay. Yes. So for the drive stage, I wonder what the stream looks like. Cool. My hair's really long, so it's like, long. I usually don't have my hair this long, but let's see. Oh yeah, I also don't run a display manager. I just have part of my bash, or no, it's not bash RC, but I made just a custom system D process that waits for something, and then it launches the display target. Yeah, and then that runs after the TTY launches, but the TTY doesn't log in automatically, and so I just changed that. Oh, bro runs start X manual. That's crazy. No, I have it where it has a nice little boot sequence. And then everything inside of Hyperland, I just use the Hyperland config to launch like Slack and Discord automatically, instead of having to worry about that. I like I'd say Rust is my new want to learn language. I'm not very experienced with it yet, but I'd say C was pretty cool. I'm studying major. I'm studying electrical engineering. Hyperland is cool. Yeah. It's very nice. Okay. So, according to ChatGPT, okay, let's see if it remembers what I was talking about before. It might not. Pierogi? Who's that? Pierogi? I don't know if that's a person or like a place. And then DWM, I've heard of DWM, but I've never used it. Evening engagement patterns? Oh, I don't understand what that means either, but I assume it has something to do with the live stream on Halloween. Which year? I'm a junior now. Yeah, it's actually so cool. Like, I feel like I'm quite interdisciplinary, and so you can. It feels like you can conquer the world because you can make anything, right? And you don't have like. It's like, oh, you need to program it. Oh, I can do that. And then you need to like design it mechanically. Oh, I can do that. And, like, it's very empowering, you know. What subjects do you have this year? I'm taking like an electromagnetics class, biology, because that's required, signal processing, and intro to probability, because that's also required. And then after this semester, it's like all my required classes are pretty much done. Recompile for DWM. Oh, that's crazy. Yeah, I didn't go too deep into the ricing thing. Okay, so no, oh my god, it doesn't understand. Okay, well, I'm just gonna have to go back up here because ChatGPT is not working properly. Okay, let's see. So, oh, here it was. So my conduction loss is going to be about half. Yes, this is like a makerspace over at MIT in one of the buildings. So yes, so the power is going to be about half of conduction losses. So that's about 7 now. But the switching loss is going to double because now that I have 2 FETs in parallel, they're going to charge and discharge slower, which means the switching time is double. And so that's probably going to be around, I don't know, 7. COSS loss, that's going to double. I mean, these are all minimal. Like, your gate drive loss is going to be really low anyways, unless you're doing some crazy currents, right? Like, it's not going to matter much. Total per MOSFET. Yeah, this is super chill. Let's see what oh yeah, honestly I think Claude usually gives sometimes better responses, but that's okay. Oh my god, so some of y'all have the most cursed configs. I just did it once and didn't want to worry about it, you know. How much of it did you do out of pure enjoyment? I mean, I'd say it's all necessity, right? Like, my parents never forced me to like do any projects or anything, and none of them were school related. So I was just like, we ball, and why not? Because I just found them interesting, and like the stuff I learned though, like I wanted the main focus was the project, and then I wanted to just do it, and so sometimes I didn't know stuff, and so the learning was like kind of a had to, but also like part of the fun. So I was like, oh, I don't know how to do this, but I'm gonna learn it to do my project. And then I would just watch some YouTube videos, because I learned like pretty well from watching YouTube videos. Okay, yes. So yeah, with 2 FETs, I divide the conduction in 2 and multiply the switching by 2, which comes out pretty even, because usually you want like half conduction, half switching. And so then it comes out to like 40-40, which is perfect. Yes. Sweet fire. And okay, it should say it didn't recalculate the switching time. But the switching time will double. So if I go back to my MOSFET, here's like the data sheet. Yeah, a lot of electronics, actually reading these data sheets, it becomes quite useful. But once you kind of know what to look for, like this graph, I look for a lot. I never look at the rest of this stuff really, because some of this stuff is like, if you're operating in like, or you're not, like normal operating regions are like quite simple math, and you don't worry about the curves. And like the number I'm looking for on the total gate charge, and it'll tell me somewhere. Oh, gate charge total. So we'll say 200 because it's quite rangy here. So 200 nanocoulomb gate charge, and because I have 2 FETs in parallel, we're going to call it 400. Well, actually, I could just do the math here. So 400 nanocoulombs at 4 amps is going to take about 100 nanoseconds. And it'll semi-turn on for part of that, but let's see what it says. With 4 amps gate drive. And it should tell me 100 nanoseconds. I'm thinking. Let's see. You know, sometimes I just hope ChatGPT gets it right, and if you prompt it enough times, you just take the average of what it says and you assume that to be true. Well, no, not really. Like, I know where these numbers should lie, and like, I know if it's giving me the right-ish stuff. And at the very end, I do the math once I've like kind of finalized the design of what I want. Oh, well, thank you. And I mean, well, oh. Let's see. Yeah, the gate charge loss is like minimal. And actually, if you look at this graph, or this graph, like the MOSFET actually does turn on after a little bit, but it only semi-turns on. So you really do want to hit the 200 nanocoulombs of like on. And based on this also, by saying that it'll switch that long, wait. Oh yeah, that's fine. That's fine. Okay. Yeah. So each, and actually, I'm giving all these numbers as if these two were like one MOSFET, because then it just doesn't have to worry about the whole parallel thing and get confused. So yeah, that's reasonable. 10 watts. So the really cool thing is that, let's see, what's my resistance? Is 0.0007 times 50 times 50. Yeah, like at full power, well, let's say 10 kilowatts. At 10 kilowatts, it's going to be dissipating like 25 watts. And so that's like, I think that's like 99.9% efficiency. What is 25? Something like that. Pretty efficient. Oh yeah, nominal distribution of the ChatGPT responses. 99.7% efficiency on the drive. I mean, that's like idealized. So realistically, I'll have like other like wire losses, but I think it'll be like 99, 98. Hello. Yeah, it should be pretty good. Oh, we have a lot of viewers. That's pretty cool. Everybody's interested, which is nice. Okay. So after doing all this math, like it's not a terrible amount of math, but it tells us that we probably do want around a 4 amp gate drive, and 3 amps is not the end of the world, because then that'll be about switching losses are the same as conduction losses. But now that we know kind of what gate driver we want, we can go shopping. Yeah, and actually before I leave, well, no, I was just saying before I leave this page, I'll write some part numbers down, but I'll worry about that later. Okay. So, usually it's under here, gate drive. Well, let's see. Oh wow. Oh wait, no, that's. Oh, this is. Let's look at this. So, oh, this is not. See, some gate drivers are not meant for like 2 MOSFETs. They're only meant for 1 MOSFET. But we want one that has like the high and low side. Like, I think this one. Usually they come in the SOIC 8 package. Yes, we're talking about power loss. So this is all heat. I do not have ChatGPT Plus. Oh, the video's expired. Oh, I should probably update that then. You know what? I'll probably just do that right now. Give me a second. Server settings, server profile, invites, create my link, copy. Oh yeah, and the YouTube video is doing a lot better than I thought it would. Well, I mean, I didn't know how it was gonna do. I mean, Leong, my friend Leong, got like 1 million views on his, but that's still pretty crazy. YouTube Studio. Okay, let's see here. I think I just go to content, this one, edit, boom, voila. And I think I just hit 1,000 subscribers. Let's go back. Dashboard. Oh yeah, look at that! I had 1,000 subscribers, guys. That's crazy. Okay, here's the new Discord link if anybody needs it. How much productivity does Livestream? Oh, I've not been very productive, but that's okay. I think this is interesting to give a test out. But somebody asked how old I am. I'm 20. Oh, somebody's going to bed. Oh, well, good. See you later. Good night. What power inverter used for? What is it? Power? Oh, it's used for my very big electric motor that I found. Yeah, so at Miters we kind of just like find stuff, and we you know, you get what you get. And I found this one. It's very nice. I think it's used for like paragliders or something, and that's why it has this part. But I'm just gonna machine this part off so I can mount a sprocket that's like closer to the front. Yeah, 12 kilowatts is gonna be so much fun. What monowheel is it? Oh, I have a CAD here. So let me. I made a little sketch of a stick figure. Wait, no, that's not it. Yes. So the stick figure is not perfectly to size, but imagine this is like you and you're sitting in it, and like that's the battery, that's the flywheel, that's the motor. That motor is like this big for like size reference. And then it's basically just like a sprocket gear kind of, or like this is an involute gear, and it meshes with this involute gear, and then it's connected to this sprocket, which has a chain that connects to the motor. And yeah, you just kind of ride in it, and it has a steering wheel to like do the leaning stuff. Oh yes, the kit car, I think they went up in price a lot, like just the base kit, but it's a super light SLC. And the funny thing is that actually a lot of people get this kit, or not a lot, but like it's not like super it's not like it, like there's a lot more people who get it, and because you can't buy it finished, it's like a kit, a lot of people don't finish, because it took me and my dad like 6 years, and so there's only like 50 of them that are like actually finished, which is pretty crazy. But yeah, I think the kit's like $50K, which is still pretty expensive, but for like in comparison to like the type of car it is, like it's insanely fast because it's the whole chassis is aluminum. It's like for what you get, I think it's a pretty good deal. Because it's almost like some people say it looks like a Pagani, and actually you can put whatever engine and transmission you want. So I saw this guy on Instagram who put like a rotary engine in it, and it sounds like a Formula One car, which is pretty crazy. Thank you. And then actually, there's a guy who lives here in Boston, who is very rich and is like, he bought the kit, but like we got the kit and we just like wanted to get it working right, and like we put an LS3 engine in it, which is like pretty nice but nothing crazy. But this guy's like hiring F1 engineers to do like some of the aero for him. It's like, that's like crazy. Like me and my dad like just kind of did whatever like to get it nothing like professional, but it came out pretty nice. So yeah. Oh yes, so for the drive stage, we were shopping. That's right. Okay, so this one did not load for some reason. I guess that data sheet just doesn't exist. Oh wow. See, these are some nice gate drivers. See, these are the isolated ones. So they have a whole isolation layer, which is nice because like it's good for like really high voltages. But I mean, I don't really need that. And low-key, this one probably costs like $10. Oh, it's only $1. Okay, that's nice. Usually these, like, all these chips are so cheap. This is why whenever I see electronics and somebody's trying to get me to buy it, I'm like, that's way overpriced. Because if you make it yourself, like each chip, these are expensive chips and they're like $1. But like a capacitor is going to cost you like 1/10 of a cent, which is just pretty funny. Oh yeah, this room here is a makerspace over at MIT, and we just build a bunch of random stuff. Yeah. Okay, where was I? Gate drivers, yes. Okay. Yeah, I'm looking. Seems pretty convincing, because I'm gonna find the current. Oh wow! Wow, if you look at that, so CVDD is 10 microfarads. What even is that? Oh, the problem with these gate drivers is that they need isolated power supplies. So you can get these small little circuits. I don't know if we have one, but that are isolated DC converters. But the problem is that then yeah, it's just cooked. So the cheap way of doing it is to use a capacitor, which like stores energy. Like to charge the MOSFETs. And if we take like 400 nanocoulombs and we convert that to a capacitance, I think it's 400 divided by 12. I'm not 100% sure. Any plans for after school? I think I'm probably going to try to start a manufacturing company. 33 nanofarads. Gate charge. see here. So yeah, I might just need an isolated power supply instead of using the capacitance. I don't know why it's writing code. It should not be writing code. Well, I'm gonna go to the restroom and I'll be right back. Alright. Let's see here. What did it say? What even is it saying? Oh wait, that's 33 what? Nanofarads? Really? That's small. That's a lot smaller than I thought. I thought it was about to say microfarads. If your control can guarantee regular low side intervals, always happen with let's see what it says. Oh yeah, switching power supplies are cool. Actually, I went down this rabbit hole a few months ago, where the way to make a actually, let me just pull it up. I have so many windows open right now. I feel like my computer's gonna crash. Yeah, I think it was here. Yes. Okay. So I was open anyway. Yes. Okay. Yes, I was experimenting around with making my own buck regulator from just like passives, and I did use some op amps, but that's about besides the point. And interestingly, all like modern DC or like DC power supplies, or this is just a DC regulator, but technically it's the same thing because you just rectify the wall and then you put the rectified wall into where VBAT would be. Oh, this is also synchronous because I use a totem pole, which means 2 MOSFETs here instead of a diode, which you would usually see before that. But what is it? I'll just make that bigger. Yeah, the interesting thing is that the current and the way they control these modern switching regulators is you actually control the current, and then you control, like, the first loop is you just control the current of the inductor, and then you feed into that the signal that's trying to get the right voltage with that, and so you get very good transient response and you get basically free current limiting, and so you get like the current and voltage limited power supply. Yeah, and so this is kind of what it would look like with like passives. And interestingly, another part of it is the control theory, because this is the current sense amplifier, which it's measuring across this inductor, or I think this, I forgot exactly which one. No, across this guy right here. And you first of all need to gain it so the signal is larger than the actual dropped resistance, and then I think I deleted the actual compensation network. Yeah, I think I did. But if you combine the right, like you have the op amp and you put like 3 RC networks in the feedback loop of it, you can basically create the right circuit to make it stable. So it's like the PID, but like using an op amp, which is really interesting. This is all just me working on it by myself. This was like at the beginning of the year I was messing around with this because I wanted to make my own regulator for my BMS, but then I realized that I should just use the regulator ICs instead of trying to do it with op amps, because there are chips that basically do all of this, like all this bottom part inside of one package, which is like super convenient, and there's no point in really doing it yourself unless you're trying to learn how to do it. And it's also not as efficient because if you make things smaller, they get better. But yeah, that's like that tangent. Now I think I'm gonna go back to shopping or seeing what. Oh, interesting. Oh, that's okay. Like making your own power supply, even like yet a simple one, would be like a really good place to start if you want to learn like power electronics. Yeah, but yeah, I would definitely not recommend making it with passive specifically, but just making your own regulator with like the regulator ICs. You still like have to figure out how to size like your inductor and your capacitors, and like that's a great place to start. See, this is a great example of it has no idea what it's talking about. Starting manufacturing. Oh, any specific industry product? Not really. Like I have this idea of like you can make these CNC machines and like CNC mill, CNC lathe, surface grinder, and stuff into like almost like Minecraft, where they're like specific sizes, like 500 by 500 by 500 millimeters. And you can basically make a factory as like a grid, and then you have machines on top that can move along the grid, kind of like rails on like a train on train tracks. And you've basically built a standardized factory, and you can just add machines to it because it's just like it's like a grid. And I think probably making small parts out of like steel and like maybe making probably like small steel parts to start with. I decided I didn't really want to go with aluminum things. Like, it'll be able to do aluminum, but I really want it to be able to make steel parts, because you're never going to make an aluminum bearing, right? And like, steel is like the foundation of like building things. Like, you're going to have aluminum steel screws. You're going to have like, everything is like to the foundation steel, pretty much. That's the best way to start, I think. You know what? It doesn't know what it's talking about here. Let me. I'm gonna find a photo real quick. The problem is that when you do the type of control that I want to do with this. Wait, let me see. Yeah, I'm not sure, but well, actually, let's look at what. Well, Vesk definitely does that, but okay. So there's some types of motor controllers where if you're not, if the motor's at stall and it's not moving, then I guess what it is that if you're at your maximum speed, then the phase voltage has to be really high for the current to go. But that doesn't really happen, I don't think, unless you're spinning the motor at crazy high RPMs. And so I think I'll be okay with it's fine. It's totally fine. So I'm not going to use this type of gate driver. I'm going to use a different type. I got that figured out. I wonder if, there's still people. Oh yes, I do have to go soon because I'm going ice skating with some friends. But I do want to finish shopping for this part. See, here's where you find the battery management ICs from earlier. They also have DC to DC converters. Well, it doesn't show up here. Okay. Well, these are all for IGBTs. See, if I click there. It's not really. Let's see. Gate. Motor drivers. See, sometimes they organize things not very well, but that's okay. So we're gonna look for these, and I'm looking for like a 4 amp gate driver. This one looks good, but see, this one is probably only for one MOSFET. Yeah, this is for one MOSFET. We need one that has like a matched high and low side. And so, oh, this one looks promising. Oh, and it's only 43 cents. Oh, very nice. Okay, yeah, there's some more down here, but they're either more expensive or they're not enough current. Oh wait, this one looks promising. Oh, that's too low side fence. Let's see. Yeah, this one might be oh. Yeah, no, this is not. See, that's only low side. Oh. There is half bridge here. Okay, that's nice. Oh, actually there are some as well that you can find that are 3-phase bridges, which is pretty funny. Like, I think this one is a 3-phase bridge. And it has basically 3 gate drivers in it, all in one package, which is pretty cool because it's like 3 chips in one. But the problem is, I don't think. Oh yeah, I've just gotten used to like seeing so many Chinese letters, even though I can't read it. You just have to look for the numbers. But yeah, it doesn't do enough current. Is the sad thing. That's not enough current. See, this is getting close. This is a 2 amp gate drive, but not quite. I remember I was shopping the other day and I did find a 4 amp gate driver. Oh, here's one. It says 4 amps. Let's look at it. Okay. Looks good. Okay, see, these just go to crazy voltage. This can go up to 725 volts. Like, I'm running it at 100, so it's totally fine. Yeah, and this is like the typical circuit you'd see for the boot capacitor setup. And then let's look at the current. Oh, what's up, George? Dude, I'm doing a live stream of me designing an inverter. And we're looking for gate drivers right now. It's pretty funny. Yeah. But I'm probably going to go soon. Okay. Let's see. Pulse width is less than 10 microseconds. Charge 400 nanocoulombs. Oh, okay, well, I don't know why I'm doing that math again, but basically this gate driver can do 4 amps at a pulse of 10 microseconds, and our pulse is like 100 nanoseconds, so like this is totally chilling. This is totally fine, but I'm gonna keep looking either way. 1.5, 500. Oh, here's another one. Seems a little less sus. Oh, see, this is min 2, so that's more sus. So, oh well, Georgia left. Oh wait, this is like a 3-phase bridge. Oh, Maddie, I'm doing a live stream of me designing the inverter.
One second. Okay. What?
Oh, I'm doing a live stream of me designing the inverter.
You're doing a live stream of you designing an inverter?
Yeah, live streaming on YouTube.
Yo,
And I have
can
13
see-
views.
What progress do you have?
Not very much. I've been so off task, but I've decided what power stage I'm gonna use, and I'm gonna use 2 parallel FETs per thing, and
Hey,
2
what's the
1
part
ohm.
number? 2 1 ohm? Surely not.
Oh, 1 milliohm.
Oh, okay.
The part
Okay,
number.
15 milliohm.
These are. I honestly might have lost it. Oh, it's these by Infineon, I think. Is this the right one? Yeah, or this one or the 1.2 milliohm
Yeah.
variant. And I'm gonna use for the power stage. It's gonna be aluminum PCB, so the
Yeah,
cooling
that's,
is
like,
going
the correct choice.
the underneath. Yeah.
Yeah, like big planes and then a heatsink underneath. That's.
And then I'm gonna put the logic stage on top of this.
Are you just copying the VESC?
No,
Are
what
you
do
just
you mean?
copying a
No, not
75-200?
really. I mean, I guess kind of. Or the drive stage is going on top. And so right now I'm looking for like a 4 amp gate driver.
4 amp.
Yeah.
That sounds a little small. What are you
Really?
What are you looking at? It doesn't. It's not ending up isolated, is it? No, it's not.
No,
That's not true.
it doesn't need to be isolated. That just makes it way harder. Oh yeah, by the way, this is Maddie.
Oh, hi, chat. For the interview or whatever.
Yeah, is anybody in chat right now? Well, chat looks a little dead right now. It's been dead for 5 minutes, but yeah, Maddie made the Tesla coil. That was
Oh
in
my
the
God,
YouTube
it
video.
was-
And
Wait,
the
the
trike.
Tesla coil was in your YouTube video?
I put a few snapshots in.
Interesting.
I was
It
like,
was too long for
it
me
wa-
to watch the whole thing.
yeah. Somebody in chat says we're alive. Yeah, the video was too long, but or somebody in chat said they were alive. So
Oh, this is like falling apart now.
what? The bandsaw?
The-
Oh yeah. Okay.
Okay, for gate drivers though, you gotta
Do you think 4 amps is too small?
know. It should be fine. I would suggest using a gate driver that doesn't have integrated bootstrap components.
Oh yeah, these have external.
Yeah. This is not a feature, to be clear. Usually
Wait,
having
you-
the components integrated is a feature.
Wait. Why? But you can't even have an internal capacitor, can you?
Well, you could have an internal resistor and diode. That's usually what they do.
Oh, I see.
then
But
you
those
just
usually kind of suck.
Have an
right?
external capacitor. They work good for low gate charge FETs. You don't
Oh.
have low gate charge FETs.
Oh yeah, no. I
You
have like
an external diode and like a 1 ohm resistor and whatnot.
I think the total gate charge is like 400 if you
Yeah.
think of both of them combined.
Yeah,
Well, there was
Unlike the first iteration of my silicon carbide Tesla, whatever, I tried using a gate driver that had like integrated components, and it was not nearly enough.
Oh really?
Yeah.
Oh yeah. This is what it looks like. It's like external
Yeah.
and stuff.
Do your FETs have Kelvin sources?
Nope. They're just normal MOSFETs. Or
Fair enough.
because you can. I think the gate. Like I'm only driving them at 12 volts, but the gate source voltage threshold's
Why are
20.
you only driving them at 12?
Because it plateaus, you know, like you get marginal extra if you drive it at like 15.
No, you should drive it at 15-ish.
Why?
Because there's a variety of things that can affect the gate voltage.
Wait, but I'm not even switching that high voltage though. So the
Like-
coupling's not as bad.
I guess the Miller capacitance isn't really a problem for that, but like, I don't know, it's just better to have more margin, you know? Like if you're at 12 volts on the gate, theoretically you have the highest performance or close enough to it, but then if something couples into your gate and reduces it by a volt or two, then you start increasing VDS a lot.
Well, I mean, I have like reasonable threshold. I think I have like 3 to 4 volts. Is
like
that not
what-
enough?
What reason is there to not have higher?
Because this is going to be the gate drive voltage is also going to be the auxiliary voltage of the car,
The auxiliary voltage of,
like that powers all the LEDs and stuff.
well, LEDs can't run off 12 volts anyways.
Well, but I mean the. You know, like it's so standard. Like 12 volts is like the car battery and all the car
Well,
accessories.
you're not making a car.
Yeah, but like you can put the car stuff on it. You're like, you don't think
What
so?
car stuff are you putting on?
I don't know, like LEDs, headlamps.
Like it's gonna fall apart immediately. I don't know.
So do you think I should bump it to 15?
I think you should.
Wait, but at the same, well, I guess 15 gives me 5 below, 5 over, right?
Yeah, I think you should bump it to 15. Nothing bad happens if you go over 20 unless you're using like 6 FETs. You can go to 30 probably pretty safely.
I'm not gonna go.
Would not recommend. The old Tesla coils used to do plus minus 30
Oh, really?
gate voltage on the IGBTs.
Oh, that's crazy.
Because if you're pushing like far above the rated current, it makes a difference.
I see. Oh, okay. Interesting. Okay,
But
well,
yeah, I
my
would say
car's
do
going to run
15.
15 volts then.
And then, like, I don't know what stuff you would put that you wouldn't want to just make custom, you know? Or I don't know how you plan to build it.
Well, also, I was planning that the STM is going to be powered off of a buck regulator from the gate drive voltage.
Yeah. Wait, you don't mean a buck regulator to 3.3, do you? Because don't do that.
Buck to 5 and then LDO to 3.
Yeah. Okay.
But isn't 15 to 5 kind of harsh?
No.
No?
That's fine.
No, really?
Or how much current does the STM draw?
I don't know, like
Like,
500 milliamps?
no, it does not. It does not, no.
Wait, like 200 max.
No, like,
Okay, 100.
you're still like an order of magnitude too high.
No. 100 is reasonable. If you like max out every peripheral, it gets to like 100.
Are you maxing out every peripheral? What peripherals
No.
are you drawing current from in the first place?
Like nothing?
Yeah.
That's true.
You'd probably be fine with like 100 milliamps max for the LDO.
Wait,
like,
so do you think 15 is fine all around?
yeah, just stick a 7805 on it and it'll be fine.
Oh, so did you say LDO from 15?
Yeah.
Oh,
I would do LDO from 15.
One of my friends said it got a little warm.
It'll get a little warm to the touch. It'll be fine. It, like, silicon can go up to 100 degrees or whatever.
Hey guys, the line does not concern himself with heat dissipation.
Or like,
I agree.
yeah, I usually do. Like on this one, I have like 15-ish volts for the gate drive, and then just that LDO to drop it down to 3.3.
Oh wow.
And this is fine. If you
Dang.
want to be all efficient about it, you can use a buck. This gets a little bit warm, not enough to matter. And if you can also just put like a TO220 7805, and then that'll dissipate a lot more heat better than that.
Yeah. No, like I think half a watt is not going to do anything in comparison to the I think it's going to be around like 30 watts or something getting dissipated by everything else. Okay, so we're going with 15 volts. Wait, but am I really gonna have that much noise?
It's better to be safe
Okay, that's fair.
because like there's.
Leong did say his inverter had a lot of noise problems, but he is switching 600 volts.
He is also switching with stick FETs, and I don't know how much I trust this ability to do stick FETs properly. I can't do stick FETs properly.
That's funny. Yeah, he said he had a bunch of EMI problems.
Well, stick FETs switch so fast that like there's a lot of really high frequency content, so any amount of parasitic capacitance will couple noise into everything.
Wait, what if you just like put more resistance on the gate?
Yeah, then it just has more switching loss.
Oh, I see. Well,
I am messing around with the sick FETs I got from the guy in the Czech Republic.
oh, nice. Nice. Wait, so at the end of this, we were saying that, that 4 amps is okay.
Yeah, that's fine.
Oh, it's actually nice. It lands right in the middle of the gate driver recommended operating conditions.
What were you talking about using, like switching to a 16th inch of something? What was that about?
Oh no, yeah, well the thing is that I'm just gonna add a lot more material of 16th inch than a little bit of 8th inch. So it's like the mass is the same, but it's distributed out more, so you get better like handling.
This sounds sus to me.
It's fine, it's fine. Oh, somebody's asking about the
One
H
strip
drive.
of 16th inch fails, and then the other one fails afterwards.
I'm gonna weld it all together, so we'll see. Oh, these are all half bridges. These are not H bridges. They're because I have 2 in parallel. So I have basically 3 of 4 MOSFETs that make up 3 phases. It's just so I get double the current, or basically half the resistance. Yeah. Yeah, well, I am probably gonna go now. I will see y'all. Let's see if I can go back to chat. Where is chat? Well, thank you. Okay. Yeah, oh, we still have 15 people viewing. Well, oh, this is just a personal project. Yeah. Just trying to make my monowheel and ride it around campus for fun. Yep. Mhm.
Tribute to the long history of making death machines here.
Oh yes, this club also has very, as Maddie said, making crazy stuff. Yep. All right. Now I have to figure out how to. Oh, I think I just sit here. Oh.